We got some good stuff on solar indexes coming up. But with that, I'll hand it over to Dean, who can say a bit more about what this presentation is and who's speaking tonight. So, Dean, go ahead.
Thank you so much, Andrew. So tonight we have we're very, very pleased to have a guest speaker. Carl, apologize if I mangle your last name. Carl Luetzelschwab, K9LA, retired in 2013 after 41 years as an RF designer and engineer with Motorola, then with Raytheon/Magnavox. He designed solid-state RF power amplifiers. So, Carl, I'm going to invite you to join us in our maker group because we are embarking on a conversation about RF power amplifiers for our currently 5-watt QRP rigs. So hopefully at some point you'll be able to join us and help us think through that. Our topic tonight is on amateur radio propagation, and Carl's got a terrific website on this and tons of articles and blog posts and videos and instruction on information about propagation and sunspot cycles. So, Carl, we are very pleased to have you with us. And with that, let me turn it over to you.
Well, thank you, Dean, and hello to everyone. And also, I have to say congratulations on being the Club of the Year from Hamvention. That's great. So can you do a repeat next year? Yeah, okay, we'll see. Okay, let me share my screen here. So what we're going to talk about tonight is the sun, the ionosphere. That'll go pretty quick because I won't get very deep into that. And then most of it's going to be space weather. And of course, got to talk about cycle 25 as things are looking up for cycle 25 at the moment. So what I said was the sun and the ionosphere, talk about solar cycles too a little bit, space weather, and then cycle 25. So solar radiation, well, the sun emits electromagnetic radiation at many wavelengths, and that's what that graph on the left shows. Goes from very short wavelengths to very long wavelengths. The most intense radiation, well, is at visible light wavelengths, and of course that's why our eyes are sensitive to 400 to 700 nanometers. Now, in relation to ionization, the energy of a photon of electromagnetic radiation is inversely proportional to its wavelength. In other words, the shorter the wavelength, the higher the energy the photon has. And what that means is when there are atoms and molecules in the atmosphere, the photon needs a minimum amount of energy to ionize either the atom or the molecule. In other words, strip off an electron. Now, the important range of radiation for our amateur radio HF bands is very short wavelengths. And if you follow that green line all the way over to the left, that's where the ionizing wavelengths are that create the ionosphere. And it consists of extreme ultraviolet, you've probably heard of that, and also X-rays. They also ionize the lower regions, and we'll get into that in a little bit. One thing you should note is where 10.7 centimeter solar flux is. It's way over there on the right. And what that tells us is 10.7 centimeter solar flux couldn't even ionize its way out of a paper bag. In other words, it's a proxy for the true ionizing radiation, just like sunspots themselves are proxies for the true ionizing radiation, which is very short wavelengths. So here's a simple conceptual drawing of the regions of the ionosphere. I put layers in parentheses because you see that quite a bit. People talk about layers. And that's kind of what that sketch suggests, that there's an F region, F2 and F1, there's an E region, there's a D region, and it kind of seems that there's nothing in between, but that's not true. there's really a continuous electron density as you go from the top of the ionosphere down to the bottom of the ionosphere. So it's better to talk about them in terms of regions. You can see during the day, the F region consists of F2 and the F1 because it does split up a bit. There's an E region and a D region. When we transition into night, there's just an single F region, and there's an E region. The E region is significantly less, but it's still there, and it can affect 160 meters and even 80 meters at night during the winter. The D region at night, for our HF purposes, goes away. So that's why it's not shown there on the left. And there's just the three bottom bullets. Extreme ultraviolet is responsible for the F2 region. X-rays between 1 and 10 nanometers, that's pretty short, result in the E region. And even shorter X-rays and also Lyman alpha spectral line of hydrogen results in the D region. It's a pretty simple view, and but it does show what the ionosphere looks like. And of course, free electrons are what is important for skywave propagation. And a free electron comes from a photon of, for example, extreme ultraviolet stripping an electron from a neutral atom, or molecule. Here's some general characteristics of the regions. The F region is roughly from 150 to 400 kilometers, a pretty wide range. And during the daytime, there's an F1 and an F2 region, like I mentioned. The F2 region is the highest. The F2 region is really a peak in the electron density. The F1 is mostly just an inflection point in the electron density profile. It's not that much of a peak. The F2 region has the highest electron densities, and of course that's best for the higher bands, 15, 12, and 10. The F2 region is the most important for our long-distance QSOs. The E region roughly extends from 90 to 150 kilometers. It has a peak around 105 kilometers. And because it is lower, if a signal refracts off the E region, it's going to take a shorter hop because the region is lower. It can also block signals from getting to the F region, which give us longer hops. And of course, sporadic E in the summer, we can't forget that because it really helps 10 and 6 meters, and it really did a great job this summer, the sporadic E season. The D region, like I mentioned, is 60 to 90 kilometers. It's not a peak, really. It's an inflection point. And its claim to fame is it's a detriment to propagation due to absorption, which is loss, which reduces our signal strength. Okay, solar cycles. Quickly talk about them. The picture on the top left is the sun at solar maximum. Lots of dark sunspots on there. The lower right shows the picture of the sun at solar minimum. Few or no sunspots. We saw a lot of that during our last solar minimum, and even the one before that, the solar minimum before that. So why are solar cycles so important? Well, for ham radio, they're important on the high bands because the area around a sunspot emits extreme ultraviolet radiation. And as we saw before, that ionizes the F2 region, gives us the opportunity to work long paths that are very long distance. When we have more sunspots, we have more extreme ultraviolet radiation. There's more ionization, especially during the day, and that results in a higher maximum usable frequency, MUF, which is just the highest frequency that can be supported between point A and point B on a given day at a given time. And all of that results in the best propagation on the higher HF bands. And there's a little sketch of a solar cycle. It goes from A to B to C. On average, it's about 11 years. There are some cycles shorter, some cycles longer. The rise time is faster than the decline. On average, the rise time is about 4 years. On average, the decline of a solar cycle is about 7 years. And the annotation above that little graph shows where the best propagation is for 15, 12, 10, and 6 meters around solar maximum. And of course, how much around solar maximum, it depends on how big the cycle is. Solar cycles are also important on our lower bands, 160, 80, 60, and 40. When we have less sunspots, there's less ionospheric absorption, especially at night. And there are also less disturbances to propagation at solar minimum. They're at when there are very few sunspots, which is solar minimum. And that gives us the best propagation on the low bands. And that sketch shows where the best propagation is on the low bands around solar minimum. I also added where disturbances to propagation kind of fall in a solar cycle. Coronal mass ejections, which can screw up the Earth's magnetic field, which screws up the F2 region, are most prevalent around solar maximum. Big solar flares are also most prevalent around solar maximum. Big solar flares can cause radio blackouts when the bands go dead and you don't hear anything. On the declining side of a solar cycle, that's when coronal holes really impact us. And that's the worst portion of a solar cycle, at least for disturbances to propagation. We're pretty much out of that now, and we should be quiet for a while until cycle 25 gets up there high enough when we start seeing more and more coronal mass ejections and big flares. We just had an M3, I think it was, in the past day or so. So they can happen anytime, but they're most prevalent around solar maximum. Okay, space weather, making sense of all those parameters out there. There's quite a few. And what we're trying to answer is the question, what is propagation doing right now? And there seem to be two ways to do this. You can take the more difficult way, which is translating key space weather parameters into an assessment of propagation. Or the easier way is to look at real-time data to assess propagation. And as time progresses, we're seeing more real-time data. So maybe the easier way is what you really want to do, but I think it's very helpful to understand the more difficult way. So let's get into it. In this more difficult way, what we're trying to come up with is an assessment of HF propagation that is derived from parameters from very complicated atmospheric and ionospheric processes. In other words, we're trying to simplify things. This pretty much works much of the time, but we have trouble predicting short-term events. One short-term event is the day-to-day variability of the ionosphere. We really find it tough to predict what tomorrow is going to be. And what the issue is the variability of the ionosphere depends on three factors. Of course, it depends on solar radiation, extreme ultraviolet and X-rays. But there are two other factors that come into play and ultimately determine how much ionization there is at a given point, at a given time. And those two are geomagnetic field activity and events in the lower atmosphere coupling up to the ionosphere. We kind of understand geomagnetic field activity fairly well. I'm sure there's going to be more work done on that area in the future. But what we don't have a good handle on is those events in the lower atmosphere coupling up to the ionosphere. Like I'm talking about, maybe a hurricane can send a gravity wave propagating upwards into the ionosphere, and it then modifies the ionosphere. We're doing a lot of research nowadays on these events. There are no parameters yet for these events in the lower atmosphere, whereas, solar radiation, we have the solar flux, we have the sunspot number, and a couple others. Geomagnetic field activity, we have the K index. But events in the lower atmosphere, we have no parameters yet because we don't fully understand everything. But it's being worked on quite a bit. And the result of the three factors causing the ionosphere is that our propagation predictions are not daily predictions. In other words, W60L prop, VOACAP, and whatever else, they are monthly median predictions. Median means 50% probability. Thus, our predictions are statistical in nature over a month's time frame. Once you understand that, you'll understand why it's very tough to use the solar flux or the sunspot number to try and predict what the ionosphere is doing. For example, if today's solar flux is 80 and tomorrow solar flux is 90, that doesn't necessarily mean the ionosphere is going to be stronger. So that's a whole nother presentation. Another example of problems we have is predicting very short-term enhancements, and I'll have some examples of that too later. There are a lot of websites with data. There's a banner made by N0NBH. That's his website. And by the way, I should mention that I'll send a copy of this presentation to you guys so you can do whatever you want to it. Okay. The N0NBH banner is seen, for example, at QRZ.com. It's very colorful. You can't miss it. It's on the homepage at QRZ.com. There's at many other places. Dr. Tony Phillips does spaceweather.com website. It gives lots of good parameters. It also has lots of stories about space weather, the ionosphere, and other interesting stuff. The Space Weather Prediction Center, it's part of NOAA. They're a little bit more technical and provide even more data, drilling down a little bit deeper. VE3EN has solarham.net. Lots of data there too. And of course, Dr. Tamitha has her videos, Whiskey X-Ray 6 Space Weather Woman. And she, on a regular basis, talks about what the sun is doing and how that's going to impact our propagation. There are lots of other general websites and many others that are more specific. They focus on just one parameter of space weather. So what parameters are important? There's a whole pile of them, but I've broken it into two categories. The first category are the basic parameters that tell us if there's enough ionization to refract the signal back to Earth. In other words, they tell us if the MUF is high enough. That's the solar flux index, which is 10.7 centimeters. SN is today's sunspot number. 304A, that's the extreme ultraviolet radiation at 304 angstroms, which translates to 30.4 nanometers. And of course, that's very important for the F2 region. MUF US Boulder is the maximum usable frequency at the Boulder ionoside, assuming it's the midpoint of a 3,000 kilometer path. So it's going to tell us what the ionosphere is doing right now. It's not like the solar flux, the sunspot number, and the 304A, which really doesn't tell us what's going on right now. So those four parameters tell us if there's enough ionization. The four on the bottom, they tell us if the Earth's magnetic field is disturbed and if the Earth's magnetic field is disturbed, that tells us that the F2 region could be screwed up. Generally, that means the maximum usable frequencies are lower and the higher bands kind of go away. The K index is a 3-hour index. It's a logarithmic scale from 0 to 9. If you see a P appended to it, that means it's a planetary index. A planetary index means it's from many stations. So it's trying to give a worldwide picture of the K index, not just a single station if it's just K. So if you see KP, it's more of a worldwide index. A is the average of the 8 3-hour indices. So it's a daily index. It's more coarse than the K index, which is every 3 hours. BZ, that's the strength and direction of the interplanetary magnetic field. And the Z component of B is perpendicular to the ecliptic. In other words, the ecliptic is the plane in which the Earth goes around the sun. So if it's perpendicular to that plane and realizing that the Earth is kind of oriented north-south, of course it's tilted a bit. So that tells us if the interplanetary magnetic field and any disturbances couple into the Earth's into the Earth's magnetic field. SW is the solar wind speed. How fast is the solar wind coming at the Earth, which distorts the magnetic field? So here's the N0NBH banner. It's on the left there. And it has all 8 of those parameters that I just talked about, and they're in the golden boxes. Now let's look at the range of those parameters. Going from a solar min to a big solar maximum. The daily solar flux can go from 65 all the way up to 245. So if we look at what happened earlier today, September 24th at 1833 GMT, so that was 2:30, about 2:30 Eastern Daylight. Solar flux was 87. That tells us we're a heck of a lot closer to solar minimum than solar maximum. Sunspot number varies from 0, of course, when the sun is blank, all the way up to 286 at a big solar max. Again, that's a daily number. Sunspot number is 75. 75 is a heck of a lot closer to 0 than to 286. So that confirms we're still down kind of around solar minimum. 304A is 129. Well, the 304A can vary from about 90 to 400. So 129 tells us that, yeah, we're kind of near solar minimum, that's for sure. MUF at US Boulder. In the early afternoon at mid-latitudes in the fall and winter months in the northern hemisphere, it can go from about 20 megahertz to 46 megahertz. And what it was reported today at 2:30 was about 18.7. So it's going to get a little bit higher as we proceed more into the fall and winter months. And of course, 18.7 says we're kind of down at solar minimum still. Doggone it. Okay, how about the parameters that tell us if the Earth's magnetic field is disturbed? Well, the K index, like I mentioned, goes from 0 to 9. It's a logarithmic function. What was the K index today in the 18 to 21 UTC time period? It was 3. So we're kind of quiet, not too bad. A goes from 0 all the way up to 400. It's a linear scale. The A index was 11. So that says, yeah, the Earth's magnetic was quite quiet. Okay, the BZ component goes from roughly plus 50 to minus 100. Today, at that time, it was plus 2.7. That's good. If it's large negative, that's not good. and that tells us that the interplanetary magnetic field is coupling into the Earth's magnetic field. Solar wind goes from about 300 kilometers per second to 2,000 when there's a big CME headed towards us or a good coronal hole. Today it was 480, which that tells us it's kind of quiet. It's not as quiet as it could be, but it's not too bad. Now here's a plot of solar flux, sunspot number, and extreme ultraviolet for cycle 23. Blue is the sunspot number. Red is the solar flux. Green is extreme ultraviolet between 26 and 34 nanometers. Now, what you can see, of course, at solar minimum, the sunspot number can be 0. The solar flux is down around 65 to 70. And the extreme ultraviolet is around 90 times 10 to the 8th photons per square centimeter per second. Now, what's important to note is if you go through some electron production and loss calculations, that 90 e to the 8th photons says that that's enough to keep 20 meters open at solar minimum during the day and early evening. So what we have now are some baseline values that say if we're at solar flux of 65, sunspot number is 0, and the EUV is about 90, that says the MUF still ought to be above 14 megahertz, unless there's a major disturbance. So values above those values can indicate when 15, 12, 10, and 6 meter are open, and that's what we get to in the next chart. It has the 3 parameters, sunspot number, 10.7 centimeter solar flux, and also the EUV on the left. And when all of those are at solar minimum, the MUF, again, it's a monthly median. In other words, on half the days of the month, it'll be at least 20 megahertz. And that also means on the other half days of the month, it's going to be below 20 megahertz. Unfortunately, we don't know which days are good and bad. Like I said, it's a statistical quantity. Now, as the EUV and the sunspot number and the solar flux increase, we can kind of make a good guess at what the MUF is going to be and also tie it to past solar cycles. For example, if the EUV for a long time is up in the 285 range, and if the sunspot number is up around 179 for a long time being many weeks, and if the solar flux is up around 170 for many weeks, that says we're probably at the peak of an average cycle, kind of like cycle 23 was, and the MUF could be in a fall winter month in the afternoon around 38 megahertz, which certainly means 10 meters is going to be open. Probably still too low for 6 meter F2 propagation, but that's okay. And if we have a really big cycle, there's the numbers. And of course, that's like cycle 19, which was the biggest in recorded history. I got my novice in 1961, so I came in on the decline of cycle 19. But of course, back then I had no clue as to what. I didn't even know there were sunspot cycles, so it didn't matter. I just got on the air and had a heck of a lot of fun on 40 meters. You can see the MUF can get up to 46 megahertz. That's a monthly median. So what that says is half the days of the month, it's going to be up around 46. It says on a fewer number of days of the month, it could be up to 50 megahertz, and that gives us 6 meters. Okay, the Ka, Bz, and solar wind. What do we desire for those parameters? Well, we'd like the K index to be less than or equal to 3. And if you look at that graph, that translates to an A index less than or equal to 15. We'd like the Bz to be positive. A little bit negative is okay. If it's highly negative, that means the interplanetary magnetic field is coupling into the Earth's magnetic field, and that's probably not good for the F2 region. And we'd like the solar wind speed to be not too much greater than 400 kilometers per second. Now, just remember that although the solar flux and the sunspot number and the 304A parameters may indicate there's enough ionization, the Ka, Bz, and Sw parameters may say that the F2 region is really screwed up and the MUF is lower. So you kind of have to remember that the Ka, Bz, and Sw can have an adverse effect on the ionosphere. Now, if you don't want to go through all that stuff, what you can do is get on the internet and look at the real-time data. There are real-time QSOs, real-time ionosphere data, and real-time beacons. Let's take a look at all that. Here's a picture from dxmaps.com. I selected a worldwide view. It's on 17 meters. This happened to be from April 13th this year, from 1554 to 1644 UTC. And what you can see is North America was working into the Pacific, into South America, into Europe. Europe was working, of course, into North America, into South America. Looks like going over to into Southeast Asia somewhere. And this will give you a real-time view of who's working who. And that'll tell you, hey, 17 meters is open. And if the lines extend to where you're sitting, then, hey, you better get on and check out 17 meters. You can go check 15 meters, see what's going on up there, too. There's similar info at PSK Reporter and WhisperNet. So lots of good information, real time. So don't have to mess with all those indices. What about the real-time ionosphere? Well, Kilo Charlie 2 Golf downloads ionoson data. That's what those circles are with the numbers in them. Those are ionosons kind of around the world. You can see that the world isn't covered very well, but that's the best we can do. What he does is add contour lines between the ionoson data. And what those lines show is the MUF for a 3,000 kilometer hop. Now, what it would really be nice is if you could add a great circle path from your QTH to a target QTH. Then you can see what the MUF was all along your path. Now, for short paths, for example, Florida to, Florida into South America, northern South America, you can see that the MUF is, well, gets about the midpoint. It's probably about 25 megahertz, which says, okay, 12 meters might be open. Now, this was for way back in August, but things should be getting better as cycle 25 rises. This is updated every 15 minutes, so it's very near real time and gives a good worldwide picture of what's going on with the ionosphere. And of course, the ionoson measurements will have the disturbances in them. Okay, if the MUF is lowered because of disturbances, the ionosons will measure that, and that will show up in the map here. Real-time beacons. Well, the reverse beacon network is pretty interesting. There's the URL for it. What you can do is call CQ on CW. Then you can see where you were heard in the world. There are lots of software-defined radios spread out all over the world, and they're listening all the time. And you can go in there and see where you were heard. How's that for a real-time presentation of what's going on? Another interesting thing is you can compare your signal to a competitor's signal, and that's what I'm just trying to show. This was from one of the CW Ops recent contests. Blue is me, WT9U is just a little bit north of me. He's orangish. And you can see in this time frame, he was calling CQ a lot more than I was. That's blue as me. He is orange. But you can see that we were kind of even in signal strength. But then a little bit later, he had me beat by several dB, in fact. So this is a great way to also compare two antennas that you may have. Just send CQ on one antenna, go send CQ on the other antenna, then go look at the SDRs and compare the signals they receive from you. Also, what you can do is plot what the SDRs heard, everybody. And this came from at 2100 today, UTC, which is 5 o'clock. This was 17 meters. You can see North America was working into the Pacific, South America, and Europe. So again, this is a good real-time picture of what's going on. And of course, there's the Northern California DX Foundation IARU beacons. There are 18 beacons worldwide. There's a picture of where they all are. Pretty well spread out throughout the Earth. 18 beacons on 20, 17, 15, 12, and 10 meters. So on a given band, a transmit slot for each beacon is 10 seconds. So what that says is all 18 beacons can transmit in 3 minutes on a given band. So what that'll allow you to do in 3 minutes is assess the worldwide propagation on that band you're listening to. This is all CW. There is software written by VE3NEA. It's called Pharos. I'm not sure why it's called Pharos, but whatever. But here's an interesting thing you could also do. There's a station in Italy was monitoring the OA4B beacon in Peru. And what it will allow you to do is determine if the beacon was coming in long path or short path. And you can see it was coming in long path for a while, then it was kind of switching, and then it was short path. So lots of interesting stuff going on if you want to dig deeper into propagation. But the main point is that this will tell you what's going on kind of in real time. Okay, let's get into cycle 25. I don't know how many of you have only been licensed for, 5, 6 years. But if you have been licensed within the last 5 to 6 years, you're probably asking yourself, what's so great about 15, 12, and 10 meters? I mean, most of the time there's only noise and not many signals on those bands. Well, all I can say is wait a couple of years and you'll be amazed what these bands can do around solar maximum with low power and modest antennas. First, let's take a look at the previous 24 solar cycles. And this is the maximum smooth sunspot number of all the previous 24 solar cycles. What's very obvious from this plot is we've been through 3 periods of big cycles. Cycles 1, 2, 3, 4 were kind of big. Cycles 8, 9, 10, 11 were big. And cycles 17 through 23 were kind of big. What this also says, we've been through 2 periods of small cycles. Cycles 5, 6, and 7 were certainly quite small. Cycles 12, 13, 14, 15, 16 were a little bit bigger, but they're still down from those 3 higher periods. And we appear to be in a 3rd period of small cycles. That's cycle 24. It's the lowest in our lifetimes, and it's the 4th lowest in recorded history. And of course, the big question is, will cycle 25 get us out of this 3rd period of small cycles, or will it keep us in this period of small cycles? That's what everybody's holding their breath for. Well, you can't hold your breath. We probably won't know for at least another 6 to 12 months where cycle 25 is going. Let's take a look at solar minimums in our lifetime, because historical data from all 24 previous cycles suggests that a long solar minimum results in a small next cycle. Now here's a plot of recent solar minimum periods. The 5 on the left are the solar minimums between cycles 18 and 19 through cycles 22 and 23. And all 5 of those, we got very used to the smooth sunspot number going below 20 and then rising up through 20 again in only about 24 months, 2 years. So we had very short solar minimums in most of our lifetimes. But then came the solar minimum between cycles 23 and 24, which was the last solar minimum. And you can see that's the green line, and it was almost 5 years we were below a smooth sunspot number of 20. Okay, the current solar minimum is the red line. Of course, we're not above 20 yet, but it's probably going to be a little bit longer than the previous solar minimum. Now, the long minimum between 23 and 24, this green one, gave us a small cycle 24. The minimum between 24 and 25, what we're coming out of right now, is longer than the previous minimum. So this kind of suggests we're going to have a smaller cycle. So how is cycle 25 doing? Well, there's another thing that comes out of historical data, and it says big cycles rise faster than small cycles. So what I've plotted here is green is a small cycle, 24. Its rise to maximum. The orange is cycle 23's rise to maximum, and it's an average cycle. And the blue is the big cycle, cycle 21. And you can see that, well, initially, early on, it's tough to tell what's going on, but eventually, the big cycle rose faster than the smaller cycle, which rose faster than the big cycle rose faster than the average cycle, which rose faster than the small cycle. The red data is cycle 25 to date. You can see that we're coming out of solar minimum. So any thoughts about a Maunder minimum, or it's probably not going to happen. We're going to have a solar cycle 25. Right now, it's rising similar to 24. That's good. And it's kind of similar to a cycle. It's kind of rising similar to 24. That's not too good. It's rising similar to cycle 21, which was a big one also. So that's good. I think the next 6 to 12 months will likely tell us where cycle 25 is headed. So it's either going to continue following green, or maybe it's going to kind of be in between green and blue, or maybe with a little bit of luck, it'll rise real fast and give us a big cycle. I'm kind of rooting for a big cycle because I have a homebrew 10-meter double sideband QRP rig. It puts out about 250 milliwatts. And during cycle 22, I worked a whole bunch of states and countries with it. Of course, I had a 4-element 10-meter Yagi up at 72 feet. And that helped a lot. But still, a big solar cycle is gonna get that thing on the air again. Let me just make a passing comment. I'd love to join you in one of your maker meetings. So what can we expect if cycle 25 is similar to cycle 24? Well, here's the prediction from the Solar Cycle 25 prediction panel. I'm aware of 56 predictions. 50 of them are for a small cycle. So solar scientists pretty much are of a consensus that it's going to be a small cycle. There are a few predictions for big cycle. All we can do is wait and see what happens. Now, if cycle 25 is similar to 24, 24 is on the left there. The black data is the monthly mean 10.7 centimeter solar flux. You can see the monthly mean data is rather spiky. So we further average the monthly means, and that's the smooth data. That's the purple or violet. You can see it's not spiky, it's smooth. You can see cycle 24 had two peaks. That's because the two solar hemispheres weren't working in concert. One solar hemisphere dominated, then died down, and then the other one picked up. Will cycle 25 have two peaks? I don't think anybody knows. We don't understand it good enough to make that prediction. But the green lines are where the solar flux has to be for a long period of time for 15 meters to come back on a daily basis. So we kind of still have a way to go. 10 meters, we have even longer. Now, that's pretty bleak picture. We're not going to see 15 meters open on a daily basis for maybe another year, and 10 meters for almost 2 years. But there is a silver lining in the cloud here. What we can do is watch for a big spike in the solar flux and the sunspot number and the EUV if you monitor it, or for a small spike in the K index, because both of those conditions can reward you with an enhanced opening. It's going to be kind of short, but that's okay. If you're in the right place at the right time, that's great. A great example of a big spike in solar flux and sunspot number is late 2020. And a good example of a small spike in the K index helping is the 2018 California QSO party. Let's look at both of those. Okay, here's a plot. There's the website, solen.info/solar. This plot goes from October 5th, 2020, all the way to October 23rd, 2021, a good year-long view of what's going on. The black line is the daily 10.7 centimeter solar flux. The red line is the daily sunspot number. Blue is the A index, the daily A index. And you can see at the end of October 2020, the sunspot number peaked up rather large, and the solar flux did the same thing. And we had great worldwide propagation on 15 and 10 meters for the CQ Worldwide DXCW contest. It also helped CQ Worldwide Phone and the 10 meter contest. Unfortunately, things kind of settled back down to solar minimum after that happened. But you can see what's happening now. We're getting more and more spikes in the sunspot number and the solar flux. So that tells us that cycle 25 is really starting to wake up. So we'll see what happens. I put a note on here. The sunspot number here peaked up to about 85. Solar flux peaked up to about 115. Let's look at this. The sunspot number peaked up to 125, but the solar flux didn't peak up like it did over here. So what that says is the correlation between the daily sunspot number and the daily solar flux is not too good, but it is very good for smooth numbers when you heavily average stuff. Okay, here's what a moderate spike in the K index can do. This is the, like I said, the October 2018 California QSO party. From the Midwest to California, the Boulder ionosphere, it was about right at the midpoint of the path, so it's a great indicator of what's going on. And here's the Boulder data. You can see on the first 6 days of October, including the first day of the California QSO party, the MUF was only about 20 megahertz. So that says I didn't hear any 10 meter W6s. But on Sunday, the K index spiked up. Look what the MUF did. It went to above 30 megahertz, and I heard lots of W6s. So just keep your eye on what's going on with the K index, and if something like that happens, take a look at the higher bands and see what's going on. Transmit a little bit too, because if you just listen, maybe everybody else is just listening. Okay. Sure looks like we still have a way to go until 15, 12, and 10 are open on a daily basis. So that was a good time to start thinking about antennas for 15, 12, and 10. Of course, they're smaller as you get higher in frequency, so you might be able to do it. And of course, when cycle 25 is near its maximum, you'll have lots of fun with modest power and modest antennas. If cycle 25 rises faster than cycle 24, then things will happen a little bit sooner. Even if we have a small cycle 25, there's still the possibility of 6 meter F2 propagation in the fall, winter months around solar maximum. It would be very limited, but it's a possibility. And of course, don't ever forget sporadic E in the summer. Sporadic E doesn't appear to be tied to a solar cycle. It just happens summer after summer. And of course, there's a minor sporadic peak in December. To reiterate, watch for short-term enhanced propagation on the higher bands. Check for big spikes in solar flux and sunspot number. You can see that at that solen.info/solar website. And again, I'll send this a PDF of this file so you can look at all those URLs in there. And also watch the K index and check for a moderate spike and go listen to the higher bands. And I can't stress enough, use the digital modes, especially FT8. It has a good advantage over sideband and CW. It can decode signals farther down into the noise. And because of FT8, this solar minimum period is going to make the higher bands the most active in history at solar minimum. So that's good. Until cycle 25 really gets going, get on FT8 and have a lot of fun. That's all I had. Let me get out of that. I better go check on a cat now. So have a good rest of your meeting or your get together then.
All right, 73, Carl.
Thanks so much, Carl.
Okay, bye-bye.
It was so good.
Did my audio have any problems?
I didn't hear anything, Carl. I think it was just fine. It was
You were
just
okay.
fine.
5'9". You were 5'9" here all the way, Carl.
Yeah, turn over.
Okay,
He didn't hear anything. You mean he heard everything?
okay, great. Yeah, I don't know what's going on with this PC or whatever. Okay, good enough.